Okay, class, welcome to lecture 6. Today we're talking about probability. Very commonly confusing subject to many students and professors alike. It's a tough subject. We're only going to touch upon the basics, luckily, so hopefully it won't be too bad. Okay, so let's jump in. So why do we need probability? Well, that's what we're going to talk about before we say what it is. So the idea is, so far, we've sort of just like played with data and secretly, maybe not secretly, assume in all these situations we have all the relevant data. I don't know how to spell relevant. That looks right. But that's not true in real life. In real life, you don't know all of the data for the population, which is the fancy word for the entire group that you're talking about. Instead, what we have is data for samples. So that's also what we're going to have to do later. So later we'll learn about, instead of having data for the entire population that you're talking about, you're going to have data about data from samples. So we got to learn about samples later. And apply the stuff we've done to samples instead of to populations. So it's a very subtle difference. The difference is, instead of asking the whole class for something, I just ask a couple people. And what we've been doing is pretending that we were always talking about populations and not samples. And so this is where probability comes in. So before we can talk about samples, we first need probability. And it's for an interesting reason. It's because we need to understand how likely, or what's the chances that when we get a sample, it actually represents the population. So that requires us to understand probability, because we're talking about how likely something is, or what chance it has happening. So just in a picture, here's a picture. If I take a whole bunch of, let's just say I have a bunch of like balls in this bucket or something, and I just like pick a couple randomly. So I pick this one, and I pick this one, and I pick this one, and that one, and that one. So I pick those 5. What are the chances that those 5 represent all of the balls or not? How likely is it that they do or not? That's the idea. So because when you get data, you can't ask every single person. You can't check all of these. You can only check a few. So you have to know how likely it is that those few actually do a good job at representing the whole thing. Okay, so that's why we learn probability in this class. So you're supposed to look at this worksheet for probability before you watch this lecture, just to get sort of some ideas. And then the main takeaway of that worksheet is that you should think about probability in this way. So you should think about it as something that you calculate for an event. So the probability that an event, which you name like capital E or something, the probability that the event E happens is defined by, so what we do is we call it P, and then you put parentheses of E, but I'm going to write the whole word event just to make it very clear. Sometimes we just call it this. So what is it? It is the number of ways that E can happen divided by the number of total possibilities. So we'll see lots of examples, but this is the main idea from that worksheet, whether it's rolling a dice or picking cards from a deck or flipping a coin, probability always comes back down to being this. The number of ways that your event can happen divided by the total number of possibilities. So next, we're going to learn rules about probability. And the examples from the worksheet will sort of lead into these examples that come from these rules. Okay, so the first rule is called the addition rule because it has to do with addition. So the idea is that when two events cannot happen at the same time, so we'll see lots of examples, then you can add their probabilities. And of course, because this is a math class, we have a fancy name for such a situation. These types of events where they cannot happen at the same time, they are called disjoint events. Okay, and there's lots of many examples like this that are disjoint. So for example, if I roll one dice, if I just roll one, can I, so this will be event one, which I'll call E, the little subscript 1. It will be that I roll a 5. Okay, so that's one event that can happen when I roll a dice. Another event that could happen, I'll call it E2, could be that I roll a 3. So then these two events are called disjoint because they cannot happen at the same time. Right? I can't, if I roll just one dice, there's no way that it could be a 3 and a 5 at the same time. It's just impossible. Because a dice, just to remind you, is a cube with 6 sides. So if I roll a 5, that means that 5 dots came out on top, which means that the 3 dots are somewhere else, not on the top. So they can't happen at the same time. Okay. So that means I can add their probabilities together. And what does that actually do? Well, so this is the way we do it. So first, P of E1, that's the probability that the first event happens. The probability of rolling a 5 is, well, there's only one way to roll a 5 because there's only one 5 on the dice. So remember, that's the number of ways you could do the event divided by the total possibilities. Well, there's 6 sides on the dice. So 6 is the total number of possibilities. And then probability that E2 happens will be the same because, again, there's only one possibility for E2 to happen. There's only one way to roll a 3, but there are 6 possibilities. And so the idea right now is sort of like, okay, I'm allowed to add them together, but what does that actually signify? We'll see that in a second. I'm allowed to do this just because they are disjoint, they don't happen at the same time. All right, great. So I'm allowed to add. What's the big deal? What does this 1/3 actually represent? Well, this is the big picture idea. So the result is the probability of rolling either a 5 or a 3. Either or are the keywords there. In other words, what we're doing is we're saying that the probability of one event or the other can be found by just adding up their probabilities of each event separately. That's what this rule is. This is what the addition rule is. And that's it. So what we've really done here is we've calculated this thing. It's actually the probability of rolling a 3 or a 5, which you can write, since you named those events, you can write it like this, E1 or E2. That's the benefit of naming your events, so you don't have to write all the words every time like this. Except I think I flipped them. That's okay. Okay, so addition rule. That's the addition rule. How do we make it more complicated? Well, first I'll do more examples, actually, involving the other types of probability-ish things that people often talk about. So here's another example. So this time I'll call E1 draw a spade. So that means I'm talking about having a deck. So you have to remember how many cards are in a deck, which is 52. And there's 4 suits, 4 types of cards. So the 52 is cut into 4. So it's 52 over 4 is 13. So there's 13 of each suit. If you don't know anything about cards, you should go look it up. So what this means is that there are 13 spades, because a spade is one of the suits. Okay. E2 is another event. Draw a heart. So a heart is just another one of these suits, and there are 13 of those as well. There's no overlap. So if something is a heart, it's not a spade, and vice versa. There's no overlap. So because there's no overlap, again, these are disjoint. I can't draw, if I only draw one card, it cannot be both a spade and a heart at the same time. So then we can calculate the individual probabilities of each event happening. So as I was explaining up here, there's 52 total cards. That's going to tell us that if I draw a card, there's 52 total possibilities. So that's what goes on the bottom. And because there's 13 spades, I have 13 possibilities for the event to happen. So that 13 goes on the top. And then probability of E2 happening will be exactly the same, because again, there's 13 hearts and there's still 52 total cards. Okay, so then using our addition rule, I could say the probability of drawing a spade or a heart, which I can write faster like this, E1 or E2. And what is it? Well, it's just probability of E1. Because they're disjoint, I can just add them up separately. So I got my 13 over 52 plus my other 13 over 52. Got to add fractions. Well, they already have the same denominator. So I can just add and get 26 over 52, which is a half. Okay. So now we will make things a little bit more complicated. But first we'll introduce a visual tool that people often use when they talk about probability, which are Venn diagrams. So the idea is that we visualize probabilities with these. So how do we do that? So you make events be circles and leftover possibilities outside of the circles. So for example, it's much easier if you just see an example. So if I roll a dice and I'm using a fair dice with 6 sides, then I can just decide to draw stuff however I want. So I could say this circle represents rolling a 4. And this circle represents, I don't know, rolling a 1. And there's no overlap because they can't happen at the same time. So they're disjoint events. So there's no overlap of the circles. And because I'm, for some reason, only looking at these two, the rest of the box, the outside of both of these, is just everything else mixed together. So 2, 3, 5, and 6 are just the rest of the box. Okay. Of course, I could just draw a circle for each one if I wanted to. All right. So this leads us to sort of thinking about, well, what happens if there is overlap? Because it's not happening here, but I'm sure at some point it will happen. So Venn diagrams help us with that situation. So here's another example with cards. So if I draw an even number, so the even number cards in a deck are 2, 4, 6, 8, and 10. And they can be of each suit. So you have these ones for each suit, for heart, for clubs, for spades and diamonds. So there's like a 10 of hearts, a 10 of diamonds, a 10 of clubs, and a 10 of spade, for example. Okay, and then E2 will be draw a club. So now these are not disjoint because they can happen at the same time. So for example, if I draw a card and I happen to draw the 4 of clubs, that means both events happened because it's a club and it's an even number. So these two events can happen at the same time. And what that means for our Venn diagram is we just draw the two circles with some overlap. So this could be drawing an even. This could be drawing a club. So what's this middle area then? That's what happens when you draw both at the same time with one draw, because such things exist. There's a 2, a 4, a 6, an 8, and a 10 of clubs, which are in both circles. Okay, so now what's the probability of doing this or that? It's a little bit more complicated. So before, if I was doing this or that, I could just do the probability of each one and I could add them up. But that's not going to work here anymore. And we can think about it visually, why it's not going to work using these Venn diagrams. Okay, so we cannot just add probability of E1 plus probability of E2. So let's see why. So pretend each area of the circle is the actual probability. This just helps us visualize more. So for example, I'll use some cool shading effects. Here we go. So this red area, that's the probability of event 1 happening, aka drawing a even numbered card. This blue side is the probability of drawing a club. So then what happens if I add the two areas together? That's what we want to think about. So if we add the two areas, what happens? Well, basically the whole area together should be the probability of one or the other happening. But if I just add both, what happens is we double count the overlap, aka this part. Because what we're doing is we're doing this area plus this area if we just add, and it'll count this piece twice. So what we actually have to do is we need to subtract that piece away once. So to get the actual area, we do this. So we take our two circles, add up the area, and then we subtract the middle part. So that the middle part is only counted once. And that'll be the probability of one event or the other happening when there is overlap, because now I'm not double counting the overlap. Okay, so this is exactly how probabilities work, but pictures are a little bit nicer to learn from. So now we can do this example. Probability of drawing an even or drawing a club as our two events is going to be, so if I call this one E1 like I was before, and I call this one E2 to speed things up, it's going to be the probability that E1 happens plus the probability of E2 happening, but then I got to subtract the overlap. So what's the overlap in probability terms? Well, it's when both of them happened. E1 happens and, so the keyword is and, E2 happens at the same time. So what does that mean for these specific events? So what the heck is E1 and E2? That just means I've drawn an even and a club at the same time, meaning I drew an even club. So that's really what the and means. It means you do both at the same time and you figure out what those are. Okay, so let's calculate this. So what's the probability of drawing an even number? That's what this thing is here. Well, how many even numbered cards are there in a deck? Like I said before, there's 2, 4, 6, 8, 10 of each suit. So there's 5 of these times 4 suits gives us 20 even numbered cards. So then the probability of drawing an even number card is 20, because there's 20 ways to do it, out of 52 total cards, so 52 possibilities. Okay, how many clubs are there? Well, there's 13 of each suit, so there's 13 clubs. Again, out of 52. Now, how many even numbered clubs are there? That's what I have to subtract. Well, we just look at this. There's 5 of each suit. So there's 2, 4, 6, 8, and 10 of clubs. So there's 5 of each suit. So there's 5 clubs that are also even at the same time. Okay, so this is the final calculation that I have to do. So it's 33 minus 5 over 52, which is 28 over 52, which you can reduce, I suppose, if you want. But I like to not reduce because it sort of reminds me where it came from, because if I reduce it down, I forget that it's really because of, I'm really just counting things out of 52. I'm really just figuring out how many of these things there are out of 52 cards. So I like to leave it like that. Okay. If you reduce it, you'll forget where it came from. Okay, so let's do another very similar example. Let's see. Find the probability of drawing a spade or draw a 4. So this time I'll keep it with words the whole time to try to make it extra clear. So because it's an or, this or that happening, I can just add them up and subtract the overlap. So I take the probability of drawing a spade, I take the probability of drawing a 4, and then I subtract the probability of drawing a what? A 4 spade, because it's the and of the two statements. Drawing a spade and drawing a 4 means that I've drawn a 4 spade. Because again, I'm doing one draw. So it's not like I'm drawing a spade, then a 4. I'm drawing something that is both at the same time. Okay, so how many spades are there again? 13 out of 52. How many 4s are there? Well, there's 4 of each number, 1 for each suit. So it's 4. There's 4 4s. Now, how many 4 of spades are there? Well, there's just the 1, the 4 of spades. Okay, so then this is going to be 13 plus 4 is 17, minus 1 is 16. So that means really what we're saying is that there are 16 spades or 4s, because I have to subtract when I count. If I add up spades and 4s separately, I overlap when I count this 4 of spades. So I have to subtract that one away. Okay. And then just to notice, if there is no overlap, what happens? Well, then that last thing that you're going to subtract will just always be 0. So you don't need to subtract. Then we just go back to the first type of example. So for example, probability of drawing a 3 or, sorry, not drawing, rolling. Now we're going back to dice. Roll a 3 or a 5. So we know that you can't roll a 3 and a 5 at the same time. So we know that the answer should just come from doing them separately and adding. But using our new rule, we're supposed to subtract what happens when they both occur. But what's the probability that when you roll a dice, that it's a 3 and a 5? Well, it's impossible. So this thing, there's 0 ways for that to happen out of 6 dice possibilities. So this new formula just becomes the old formula when these two are disjoint. So this is really the same as saying that the two events are disjoint in a different way. If they can't happen together, that really means that the probability of both of them happening should be 0 because there's no way for it to happen. Okay, so that's the same. In any case, you still get 1 over 6 plus 1 over 6. But now you subtract 0 over 6, so that doesn't do anything, and you still get this answer. Okay, so just to summarize the rule that we learned today, here it is. For two events, E1 and E2, the probability of E1 or E2 happening, that you do one or the other, is the probability of one happening plus the probability of the other one happening minus the probability of both of them happening at the same time, which you shortcut by writing the word and. So this means both events happen at the same time. And if the events are disjoint, then this will never happen. So this part will be 0, and you'll go back to the original formula we had for at the beginning. Okay, so that's it for this one. And see you next time.